Hi guys, welcome to the next lesson. Today we're going to be talking about the mole. So this comes under Area Study 1D, Unit 1.3, the mole concept, which we'll introduce today, and determining the number of mole of atoms in a sample of known mass. So we've talked about not being able to count individual molecules. Remember, relative isotopic mass, we had that because we weren't able to count a particular number of atoms inside that iron ruler or that iron block. So we can't count those individual molecules, they're just too numerous. So chemists have come up with a relative atomic mass to assign, help us work out how much mass would be in that particular element. Same thing with the mole. Similarly, we're not able to count the particles inside individual elements. They're just too numerous, too many of them. And it's an inconvenient number to work with. Your calculator wouldn't be able to compute, a standard calculator wouldn't be able to compute those numbers. We're talking 23 zeros. A lot of zeros to work with. So chemists have assigned a quantity that they use to represent these particles, and that's known as the mole. So we'll talk a bit about that now. So, for example, look at these ice cubes. These ice cubes have water molecules in them, H2O. Just pure water, without any impurities. These water molecules, these ice compounds here, they contain more than 10 times 10 to the 23 zeros of molecules. It's just an enormous number to work with. Doing this sort of maths, 2 ice cubes, and you've got 10 times 10 times 10 times 10 to the 23. A lot of numbers. And then it'll become 2 times 10 to the 23 if you had 2 ice cubes. It's huge. The number's too large to work with, so we needed a more workable unit. So the mole has been used as a convenient way to count units, just like a baker's dozen. So instead of saying 12 eggs, I've got a baker's dozen. So I have 1 mole. It's a unit that we can easily count and we can easily quantify the number. And it's universal, so we all know the amount that you're talking about. So the accepted way to count these particles is known as a mole. It's really just an amount of substance represented by the symbol lowercase n with an element. So let's take a look what that means. So for example, 1 mole of hydrogen atoms. It tells us there's 1 mole of hydrogen atoms. If there's 1 mole of hydrogen molecules, it tells us there's 1 mole of hydrogen molecules or 2 moles of hydrogen atoms. So the reason is a hydrogen molecule, there's 2 of them. It's a gas, it forms in a diatomic molecule. So it would look like this, with its electrons spinning around there in these paths. So that's a diatomic molecule. Whereas 2 moles of hydrogen atoms is because you've got 1 of the atoms there and 2 of the atoms. If you had 2 moles of aluminium atoms, again 2 moles of aluminium. 2 moles of calcium chloride, you would have 2 moles of calcium ions, because calcium, remember, has a 2+ charge. So if you had 2 moles of them, you'd have 2. Now in this formula, we have, for every 1 calcium, we have 2 chlorines. So if we had 2 moles of calcium chloride, we'd have a 2 in front of this number here, which would mean we'd have 2 times this subscript 2, which would mean 4 moles of chlorine ions. So what it is just a way of breaking up the different number of elements or components in the compound. This is just an infographic here. Here's another explanation of what the mole is. It's a substance which has this many particles in it, and it's defined as the amount of atoms in 12 grams of carbon, which I've already talked about. You can look at this at your leisure. It can help just decipher or talk about what the mole is and how much certain things have in 1 mole. The 1 mole of substance is defined as the same number of particles in exactly 12 grams of carbon-12. And the number has been experimentally determined to be 6.022 times 10 to the 23. So this is called Avogadro's number. Avogadro was a scientist, came up with this number that in 1 mole of a substance, there's this many particles here. And it's given by the symbol Na, capital N, lowercase a. Sorry, capital A, but subscript. Capital N, capital A, but the A is subscript. That's the amount of particles in 1 mole of a particular substance. So we've already learned that the number of particles would be this many atoms, and that's Avogadro's number. It's a big number, yes, but it makes working with a number of particles with an element far easier. So if you look at this little chem file here, taken from your Chemistry 1 textbook, what it talks about is just try and imagine Avogadro's number. It's actually, it's a very big number. So Avogadro's number is a really big number, and yes, it would take this many grains of sand, the 1 mole of sand, or 1 Avogadro's constant number of sand, will stretch from the Earth to the Sun and back 7 million times. So it's an enormous number, but the number of particles inside is huge. So it actually makes it easier to work with. This is just trying to give you another scale of the understanding of how big or how many particles are inside an atom. So if we use this Avogadro's number, we can be useful to work out a number of things. And this infographic here, or this image, helps describe that. But for example, if you have 1 mole of substance, you know it has 6.02 times 10 to the 23 particles. If you have 2 mole of substance, then you would have 1.204 by 10 to the 24 particles. You're just multiplying 6.02 by 2. So you're just doubling the number, and you would add an extra 0 here. So it would go from 23 to 24. Conversely, if you had 0.3 mole, so 3 over 10, of that substance, you would have 1.81 by 10 to the 23 particles. So what you can do now is if you have a certain amount of that particular compound, you have a certain amount of hydrogen that you have in the lab, and you want to know how many particles in it. So now you have that certain mole, 0.3 mole perhaps, of that hydrogen. You multiply it by 6.02 times 10 to the 23, and you can work out how many particles of hydrogen do I have. And this will become relevant of why it's important later. Or if you were to have even more particles and you wanted to work out the mole, so you wanted to work out how much of that substance do you have, you can now use it to help you work out how much you have. So you started with, you got this many particles, and you know that in 1 mole there's this many particles. So you have this much of the mole. So you have 0.781 mole of a particular compound. Or you have this many particles, you can also work out how much mole of that compound you have. So there's a mathematical relationship between the number of particles, capital N, and the amount of substance, lowercase n. This relationship will become used a lot in chemistry, and you see it here. So if we have the number of particles, capital N, you can divide it by Avogadro's constant to get the amount of substance, or the moles. And similarly, we can multiply the moles by Avogadro's number to get the number of particles. So I may have a certain quantity or a mole of a particular compound, and I want to know how many particles are inside there, because then I want to work something else out. That's what this formula is for. So let's do an example so we can actually get a head around this. Calculate the number of molecules in 3.5 moles of water. You're given a quantity of water. We're not given the number of atoms of water. It's too large. It's too big to count. So we're given a moles of water, 3.5 moles of water. This formula triangle over here can be helpful. I would suggest to write it down somewhere, put it in your desk, put it in your chemistry book, put it in your notes section. It's very helpful. It's a nice, easy way to work out what you need. So on the bottom, you would multiply, and from the top down, so if you go from left to here, right, you would multiply, and going from this one to this one, you would divide. And going from this one to this one, you would also divide. So top down, you divide, and left to right on the bottom, you multiply. So it will be a division over here too. So you have to find the number of molecules in 3.5 moles of water. You don't know the number of particles, so that's your X, your unknown. You do know the number of moles of water, that's 3.05, and you do know the number of particles inside 1 mole, which is Avogadro's constant. So you're trying to find capital N. So how would you do it? Well, you have to work out how to find the number that you are trying to look for. So what you do is you cover up the two that you have and you'll find the one that you need. So the number of particles would equal moles times Avogadro's constant, which is 3.5 moles times Avogadro's constant, which is that many molecules. So simply you cover up what you don't have in the formula triangle, and that will be what you need to do to calculate it. If we do another one, calculate the number of oxygen atoms in 2.5 mole of this much. So we want to find the number of atoms in oxygen. And we have a certain quantity of oxygen, 2.5 mole. So that mole of oxygen is here. Number of particles is here. We're still trying to, sorry, the number of particles in 1 mole is here. And we're trying to find the number of particles in total in this amount of mole. So what we need to find is we need to find the number of atoms, sorry, number of oxygen atoms. So 1 atom of oxygen would be like that, a single O. An oxygen molecule would be 2. That's a molecule, and that's an oxygen atom. So O is an atom, and O2 would be the molecule. So we have 2 molecules of oxygen gas. Sorry, 1 molecule of oxygen gas, which means 1 atom. So therefore, we have to multiply the number of moles by 2 because we have twice the amount of moles for every oxygen atom. So we have 5 mole oxygen atoms in total. That's the first step. The second step is now we need to find the number of particles. So again, we cover up what we know. We know the moles, which is now 5 mole, and we know the amount of particles in 1 mole, which is 6.02 times 10 to the 23. So we multiply these two numbers by each other, and that will give us the amount of particles. So 5 times 6.02 times 10 to the 23, power of 23, and that will give us 3 times 10 to the 24 atoms. Today's lesson is very important, arguably the most important lesson that you'll have in this unit. So it's very important that you do understand what the mole is, what it's representing, how to calculate number of mole, how to calculate number of particles using those formula triangles. The mole is a universal quantity used by chemists basically to summarize and create a workable unit when studying elements. 1 mole is equal to this many particles, termed Avogadro's constant. The mole can be used to calculate the number of particles inside an element based on its molar mass, which we'll come to in a bit. These are the questions I'd like you to complete, 1 to 4 of chapter 5.2, page 123 of your textbook. If you need assistance with these, go over and watch the video again, read through your textbook. It's about practicing and using this, getting used to the language, getting used to the formulas and rearranging them. Thanks for watching.